Tonight's presentation is given by Dr. Robert Donahue, former astronomer at Mount Wilson and the Harvard College Observatory, who will be talking tonight on What's Up in the Sky, Fall Edition. Bob and I worked together in different departments at the Center for Astrophysics 20 plus years ago. He was in solar and stellar, I was in planetary. Since our time together, those two departments have merged into one department. So we are no longer separate, we are together. So, Bob, floor is yours.
Okay, so tonight, this is one in a series of talks we've been doing every season, right? For spring, summer, now fall. We're going to be covering things in deep sky objects and solar system objects, so let's get started. Very quickly, in terms of why am I giving this talk as opposed to somebody else, as Gareth mentioned, I was a research astronomer for many, many years, a very, very long time ago, back when dinosaurs roamed the earth and I had hair. Most of my research was in the solar-stellar connection, which is just another way of saying, is the sun weird? Mostly we were looking for things like the sunspot cycle on other normal stars. Once the first exoplanets were discovered, coincidentally, they were orbiting planets that were in our program, so we delved into exoplanet environments. In the course of doing this, I disproved 2 exoplanets. They were just very big sunspots. Variable star research, and a little bit into asteroid mineralogy. And most of this was done at Harvard CFA or Mount Wilson Observatory or National Observatory in Sunspot. Okay, so tonight we're going to talk about things happening in the fall skies, particularly this year when we get to the solar system objects. In terms of your skill level, we're aiming this toward beginners and amateurs. You don't really need to know very much, but if you have done a little work studying the sky, learning the constellations, taking a telescope out or whatever, there's going to be lots of challenges for you to try. I really like doing challenges because then you get to really learn the sky and get to rack up some accomplishments, which hopefully will make you want to do it even more. So when we're doing observing, it comes down to 2 things. What's in the sky in a given date and time, right? The constellations all change over the course of the year, so we're going to be looking at the constellations there in that part of the slide, and also what events are happening. And typically, this has to do with solar system objects. When planets get close together in the sky, or there's a meteor shower, or an eclipse, or things like that. And we'll be breaking it down into solar system objects and deep sky objects. And in terms of challenges, there'll be things to try for without any telescope, or if you've got telescope or even binoculars, there's going to be something in here for everybody. If you are just learning the sky, the old school method is to use a planisphere, and you can buy these on Amazon. You just dial in your date and time. Remember, they use standard time, not daylight time, and take it outside, face in the right direction, look for the brightest stars, and go from there. And most of the planispheres have all the constellations, some of the brighter stars labeled, and some of the brighter deep sky objects. And this is, like I said, the oldie school method of doing it. Newfangled method is to use an app. There are lots of apps available. Most of them are free, or you pay a small amount of money to make the ads go away. I particularly recommend Stellarium, which you can also get for your desktop. It runs on everything and has everything but the kitchen sink in it. So that's a great one to use. All right, so now let's go back to the fall sky. We have looking north, looking south. Now during the summer, we were focused on the Milky Way, right? The Milky Way was going overhead right into the southern horizon. Now the Milky Way shifted a little bit toward the west. But even in the fall, the Milky Way goes through the constellations of Cepheus, Cassiopeia, and into Perseus, and we're going to be looking a lot in there. Looking south, summer constellations are over here in the west, but now we've got Capricorn, Aquarius, and everything kind of around the Great Square of Pegasus, which is easy to find, and then up here Andromeda, which we'll show in a second. One thing that's kind of cool about the fall constellations is a lot of them have water themes. You've got Capricorn the sea goat, which there's no such thing as a sea goat. That's actually Babylonian in origin. Cetus the sea monster, little Delphinus, over toward the winter constellations, Eridanus the river, Aquarius, Pisces, which you know from the zodiac, and Pisces Austrinus the southern fish. The cool thing about this is most of these constellations aren't particularly bright. Pisces Austrinus has the bright star Fomalhaut. The Great Square of Pegasus is easy to find. The rest of these are kind of dim, but this year Saturn is right smack dab in the middle of it. So it's easy to find this part of the sky. Saturn's the only bright thing in the area if you look into the southeast, the early part of the fall. The other cool thing about the fall constellations is the story of Andromeda. This comes from the Greek. Andromeda was a princess. Her mother and father were the queen and king Cassiopeia and Cepheus. Cassiopeia bragged that her daughter was more beautiful than even Athena, which made Poseidon very angry, and he sent a sea monster to come and wreak havoc on the kingdom. They offered Andromeda, chained her to a rock to offer to the sea monster to get it to stop. Perseus shows up having just killed the Medusa, shows it to Cetus, turns it into a rock, and flies away with her on Pegasus to live happily ever after. So that's kind of our myth. Clash of the Titans. Yes, the entire movie. I have just summed up the entire movie, The Clash of the Titans. Okay, going back to Andromeda and that vicinity, two of the most famous deep sky objects for this part of the sky are the Andromeda Galaxy and the Triangulum Galaxy. And when you start learning the sky for deep sky objects, and you see lists of how bright they are, these come up to be pretty bright. You know, magnitude 3.4 is naked eye, 5.7 is almost naked eye if you're in a good dark sky. But when you go looking for these galaxies in a telescope, they tend to be a bit of a disappointment. They're very dim. And that's because they're actually so close to us that these magnitudes are the integrated. It's the total light. If you could squeeze all of the galaxy down to be the same size as a star, how bright would that star be? In reality, they're actually quite dim because they're so large in the sky that the average brightness on any part of it is rather dim. So usually you want to do, if you have an imaging scope, you can get very nice pictures of it, but even then you've got to take images for a good part of an hour to see a lot of detail. Nonetheless, M31, the Andromeda Galaxy, is a good naked eye challenge. If you take your planisphere and it'll be on there, you can look in Andromeda, offset from a couple of the stars in the middle, and find it. You'll see a fuzzy patch in the sky, about the same brightness that the Milky Way is in the summer. The Triangulum Galaxy is a lot harder. If you go to very dark skies, you should be able to see it in the same way. Easier to find in binoculars. So we'll go with that. But there are other galaxies in the vicinity, particularly in Pegasus. In fact, all the way through Aquarius into Pisces, into Aries, and through Pegasus, there are lots and lots of galaxies, but most of them are very small and very faint. You need a larger telescope for them. These four are somewhat doable. And they're also not that hard to find because they all tend to be close to bright objects, or at least stars. M74 is right next to the star in Pisces. The Superman galaxy, because it has that S shape, is just below Alpha Pegasi. The Dirichlet group, only the bright galaxy is easily visible in a small telescope. The other ones require a larger telescope. This galaxy is kind of famous this summer because it had a supernova back in July. And so the supernova was about as bright as the core of that galaxy is. It's faded somewhat, but still visible if you've got a large enough scope. And then the electric arc galaxy is really nice because it has that dark lane, which you can see even a small telescope will show up. Okay. So much for galaxies. What's with all the M's, right? We had M74, M33, M31. These are all from the catalog of Charles Messier, who put together his catalog in the late 18th century. His big thing was comets. He wanted to discover comets. And so he would just scan the skies from Paris, which of course you could do then because there was no light pollution, looking for comets. And when he came across a fuzzy thing, if it didn't move, he marked it down. Because the last thing he wanted to have happen was to discover a comet only to get laughed at because what he discovered wasn't a comet. So he came up with a list of 103, expanded to 110 objects. It has most of the brighter deep sky objects, star clusters, nebulae, and galaxy, but not all of them, which is kind of weird. There's some very famous DSOs that are not Messier objects. And they only go down to minus 35 declination because he was observing from Paris, which is about as far south as we can see here. So you can see all of the 110 Messier objects. Then some of those had C's. That's the Caldwell catalog. This is a newer one done by Patrick Moore of all the things that should have been on Messier's list, but he missed somehow. And his catalog starts at the north and goes all the way around the sky down to the south with another 109 objects. So you can see about 70 of them from here. And it's the Caldwell catalog after his mother's maiden name because being Moore, he couldn't call it the Moore catalog because that would get confusing. Okay. So, going back to the fall Milky Way in Cassiopeia, Cepheus, actually going all the way from Perseus with the double cluster all the way down here to Deneb, which is one of the summer triangle stars. If you've got binoculars or a small telescope, this line going across the W of Cassiopeia and just under the bottom of Cepheus over to Deneb is awesome to look at. Just not even knowing what you're looking for, just scanning along, slowly. There are at least 36 star clusters just in this part of the sky. And you don't need to really know anything. You could just try, not even trying to have to point anywhere. You just scan, and you're going to come up one after another. Just to give you examples, here's 10 of them that I imaged with my C-star. And you can see they range quite a bit in like how many bright stars versus faint stars. Some of them, like Carolyn's Rose, is mostly faint stars. It's very misty looking. This is a really pretty star cluster. Some of them have odd shapes, like the Dormouse. Some of them are big and open, like C16 and Lacerda. Why that's called the lawnmower cluster, I have no idea. And then you've got the fuzzy butterfly, which someone decided it was a fuzzy butterfly and it stuck. Okay. One last thing in terms of a binocular challenge in this area is this odd thing called Kemble's Cascade. And you can easily find it. Go to the W of Cassiopeia, go across to the east, and then another width of Cassiopeia over, and you'll find this field. It's this line of about 15 stars in a row. These stars have nothing to do with each other. It just happens to be from our vantage point on Earth that they're just all lined up. And there are several places in the sky where you can find these things. In the summer, there's the coat hanger. Here you've got Kemble's Cascade. And it's just it's one of those things, if you're scanning along with binoculars and you encounter it, you can't unsee it. It's just there forever. Globular clusters too. In the summer talk, we saw about 20 globular clusters. They're all over Ophiuchus and Scorpius. Here there are fewer because now we're not looking toward the center of the galaxy. We're kind of looking off to the side. But there's still a few clusters up there above and below the disk. Two of them are very bright. M15 and M2 are easily viewable with binoculars. They're very bright and they're easy to find. M30 and M72 are fainter and more of a challenge, particularly M30. It's like the only Messier object in Capricornus, but it's a lot harder than it looks. I've got 3 of these labeled as immigrant. One of the latest findings from the Gaia satellite, which has been measuring the location, color, and brightness and motion of 2 billion stars in our galaxy, which sounds like a lot, but when you consider there's almost 1 trillion, we're still only scratching the surface. But in doing so, they measured those positions and motions for stars in some of these globular clusters and realized that based on their orbits around the center of the galaxy, they could not have, probably did not start with our galaxy. Globular clusters are very, very old, and the canonical thought was that they started when the galaxy was formed. What's probably happened with these three is that we collided with another galaxy. The globular cluster has started with the other one, and when that galaxy got cannibalized by the Milky Way, the globular cluster just moved in and just started orbiting the Milky Way instead. Finally, there's one bizarre little object. It's just about a degree west of M72 is M73. This is one of Messier's mistakes. There are 2 of them in his catalog, where what he's cataloged is not a true deep sky object. He thought this was a small cluster. It's really just this little Y-shaped asterism of stars. But if you're going through trying to observe every single Messier object over the course of a year, you'll want to check that one off.
What defines a globular cluster?
A globular
How do
cluster,
you know that they're not like, some of them are, let's say, 1,000 miles away, and then the other one's 1,500 miles away, but it looks like they're together. I mean, what makes them?
well, these are gravitationally bound.
Oh, they are?
Yeah, and there's 50,000 up to 500,000 or more stars depending on the size of the cluster.
That's what I was wondering.
Yeah. Why they look the way they do, I mean, it's gravity that's kind of keeping them together. But remember, they also live in the extreme suburbs of the galaxy, right? The galaxy's got the disk and the bulge. These are way up out here, going around in their billion-year orbits. And so they don't interact much. Sometimes you'll get one that will go through the disk as part of its orbit, and sort of then it'll start losing stars that way. So some of them are a little sparser than others. You can see this one looks a little bit more sparse than, say, M15. Planetary nebula. In the summer, we had the Dumbbell and the Ring Nebula. Here we've got a couple of different ones. 2 of them are small but very bright. This is the opposite of the Andromeda Galaxy and the Triangulum Galaxy that's very dim and thin. These are small but very bright. And when you find these in a telescope, they'll look like a very blue star. And then when you put some magnification on them, you'll start to see a little bit of structure. 2 of the others are large but very dim. So here you need to use a low power eyepiece and a really dark sky to see. But you've got the Helix. This is actually really far south in Aquarius. And in Perseus, the little Dumbbell. This one's, for the Messier objects, this is one of the harder ones to see because it's kind of dim and it's small compared to some of the bigger galaxies or whatever. But this is a planetary nebula. And what you have here is the central star. There it is there. There it is there. And the other 2 you can see. Throwing off its outer layers of atmosphere, which what's left is the hot core of the remnant of the star, which is heating up all the gas that it threw off. And you get different color because the different temperature as you get cooler as you go out excites different types of atoms. So red, hydrogen. This bluish color is mostly oxygen. So there's those 4. For emission and reflection nebulae, the fall is a little tough. There are lots of nebulae in Cepheus and Cassiopeia, all the way over to Perseus, but they tend to be dim, and they're big. These are 2 images of the Heart and Soul Nebula. They're right next to each other in Cassiopeia. taken with one of my telescopes, but they're so large. This is only about a quarter of the nebula. It's about 4 times bigger than what I have captured here. And for the Sol, about 3 times larger than what I have captured here. They're really, really big and have a lot of structure and dark regions, etc. The California Nebula, which looks like California if it's not on its side right now, the bright part in the top left, you can sort of see as a dim glow in binoculars. I have seen it. The Iris is a reflection nebula. What you'll probably see in a small telescope or a medium telescope is you might be able to see this. You'll see the star and this sort of bluish haze. You won't see the smoky, dark nebula so much. For that, you need to take images. But what you will see is background stars around it and this sort of a black donut in a telescope. And what's going on here is, in this case, the star is just heading through a dusty patch of the galaxy. It's not dense enough to make stars, which is what's going on for the emission nebula, but it's just going through. So you have a part that's lit up by the starlight, and then around it, the dust that it's not lighting up because it's a frontal view. In the fall, there's a couple of nice double stars. I don't generally talk about double stars, but here, one of my favorite is Gamma Andromedae. Here you've got a red giant and a blue dwarf, but what's really odd, it's always fun to look at this double star with a lot of people, because everybody seems to come away with a different, if you ask everybody what the colors of the 2 stars are, you get very different answers. And whenever I've looked at that star, it almost always to me looks yellow and green. And green's kind of weird because there are very few things in the sky that are green. Some of the planetary nebula kind of look a little green, but mostly they're blue. Uranus looks green. And that's about it. Almost everything else is blue or red or orange or yellow or white. Eta Cassiopeia is another easy to find, and they're very wide doubles. You can see them in the smallest of telescopes. Very bright white and this little dim orangey red star companion. Okay. Also talking about stars, one experiment you can do with your naked eye, not needing a telescope or binoculars, you can track the variations of Delta Cephei. So if you go back to Cepheus, which kind of looks like a doghouse, so that last star is up here somewhere. Right off the bottom, there's this triangle, and Delta Cephei is the little point of the triangle. Most of the time, it's about as bright as the star next to it, the one here marked A. However, over the course of 5 days, it gradually gets dimmer and then brightens back up again, and this repeats every 5 days, and you can follow this. And why this is important is Delta Cephei is the prototype for Cepheid variables. This pulsation that's happening, the period that it takes and is intrinsic to its brightness. So ones that have a longer period have a different intrinsic brightness, which means that if you observe a Cepheid at some great distance, let's say the Andromeda Galaxy, and you can identify that it's a Cepheid and you measure its period, you know intrinsically how bright it is, which means now you can tell the distance. And that's how they figured out conclusively that the Andromeda Galaxy wasn't just some kind of weird spiral nebula inside of our galaxy, but was in fact another galaxy 2 million light years away. But this was the first of that class of star to be discovered, and it's something you can monitor yourself from home.
Of course, there were 2 different types of Cepheid.
Yes, well, yeah.
They messed it up and got
Yeah.
a third of the distance. But
That's
yes.
true too. But another one is Algol. Algol is it's funny, it's a brighter star, but it's a lot harder. Here you've got an eclipsing variable. You've got a hot blue star and a cool red star, and they are orbiting around each other so that every 2 days, every day and a half, one gets in front of the other one. If it's the orange star in front of the blue star, you get a deep minimum, and it goes from magnitude 2.2 to 3.5, which is a pretty good range. It's easy to detect something like that. When it's the other way around, you get this very, very tiny little dip in the brightness, which probably you wouldn't be able to see with your eye unless you really got good at this. The hard part with Algol is the eclipses only last 6 hours, and the minimum magnitude is only 12 minutes. So catching it at minimum. So in Algol's case, if Algol is as bright as the star next to it, which here is marked W, you've caught it close to the bottom of the eclipse. Most of the time it's going to be, about as bright as the one marked A, or between A and N or M. I think I caught it in eclipse over the last weekend. I think that's the first time I ever have. So that's a great challenge. And this is a variable star that's been known. It's one of the first that was discovered close to 1,000 years ago. Finally, in terms of stars, a couple of, about almost 2 years ago now, there was all this kerfluffle in the media about a star that was going to explode. Go outside, look for this star, it's going to explode, and then nothing happened. And this has become a pet project of mine because I remember reading about the star when I was a kid, and it's like, oh, it's going to probably explode around 2024. And I thought, well, I'll be an old man, so I'm not going to worry about this anymore. And now it came back to haunt me. So I tried to figure out what was going on. The system itself is pretty easy to understand. You've got a red giant and a white dwarf. The red giant is slowly oozing and losing mass. Some of it lands on the white dwarf. White dwarfs don't like to get fat. They have a limit, about 1.44 solar masses. Anything bigger than that, it has to shed that extra mass somehow. And what's happening here is it starts out just below the limit. It grabs some of the material coming off the red dwarf, and then it has to do something, so it has an explosion. And then it all starts over again. And the cycle takes about 80 years for this system. And when they first come back in the media, I thought, oh, I'll bet it's I knew that it was a binary system. I thought, well, it's got to be a very eccentric orbit, and they got to have maybe an 80-year period. It's kind of like Uranus distance or whatever. But that's not the case at all. The orbital period's only 228 days. And I'm thinking, well, it's got to be really eccentric because that's what's going to trigger it. It's got a circular orbit. So that was weird. And then this guy named Schneider wrote a paper last year that says, hey guys, did you notice over the last 240 years that the explosions always happen at the same orbital phase? It's a circular orbit. How would the star care? Every day is about the same, they're always the same distance away from each other. So that was weird. So one night when I couldn't sleep, I tried to figure this out. If you draw the system to scale, it's interesting. The two stars are about the same distance apart as the sun and the earth. And on this scale, there's the sun. And the white dwarf is even much, much tinier than that dot. But the white dwarf has 2/3 of the mass. So this is a big, puffy star and a very, very small, dense white dwarf. The star is so big and puffy that it's 63 times the size of the sun. And to put that into perspective, if you plunk this star into our solar system, it would extend out to Mercury. So if you look at the distances, you get Mercury distance, Venus distance, Earth distance. Okay. And I apologize for the next slide. Oh no, I apologize for the slide coming. The other thing that you notice with this star is it has a variability. It varies like the other two stars we were looking at. It's got this nice sinusoidal period that's 114 days. That's half the orbital period. How do you get a variation that's half the orbital period, is if the star, the big red giant, isn't round, that the gravity's from the white dwarf's causing tides. So it's more shaped like an egg. So we'll see it, sideways, end on, sideways, end on, and that's why we get that variability. Okay, here's the slide I'm going to apologize for, because here's where all the math comes in. If you start plugging in all the numbers, look it up in the catalogs and everything else, you end up with this sort of picture. From spectroscopy, you can figure out roughly what the rotation period of the star is. It comes out to be, has to be less than 275 days. The orbit of the two stars from our line of sight is 65 degrees inclined. So they're going around like this, not like this. If you plug that in there, you can get it down to 240. But that star is egg-shaped, so there's all these weird tidal effects going on. And I suspect what's happening is that at some point on the star, if the star has differential rotation, which I know about because a guy that pays my bills wrote a thesis on it many years ago, some part of that star is probably rotating at the same rate it's going around the white dwarf, which means that eventually some big sunspot on this star is going to happen and be in just the right place at just the right time. If the star has a sunspot cycle, and if the sunspot cycle is longer than our sun's 11 years, and that's very likely for a giant, what I think's happening is that eventually you get a sunspot that's just hanging out there, pointed right at the white dwarf. It has a coronal mass ejection or a flare, which here, when the sun does that, we see the aurora. I think what's happening there is that's basically acting like kerosene on the flame. And that's what's triggering it. And that's why it's always in the same orbital phase when it has an explosion. Anyway, the next time it's having that phase, here's the punchline, is November 10th. So while we've been waiting for 2 years for this star to explode, there's probably a good chance that if it's going to do it this time around, it's going to be around the beginning of November. So, and if not, next June. And in November, that star will still be above the horizon right after sunset, but not much for very long. Next June, of course, it'll be up almost all night. Anyway, that's the geekiest I'm going to get, I promise. Okay, let's go back into the solar system, where we're talking about planets, dwarf planets, meteors, comets, the moon and the sun. Here are 4 things we want to look for. Saturn. Remember, I said at the beginning, Saturn's in the southeast part of the sky. It's the brightest thing out there. There's nothing else bright around it. Saturn's wonderful in any telescope. The only problem is, right now, if you would look at Saturn, you'd see something like this. You can see a nice little ball and these very thin, tiny rings, and that's like not what you would expect. And that's because Saturn, like the Earth, has seasons. So just like this month, we're going to be going into the beginning of fall. The equator is going to be lined up, equal day, equal night. The same thing's happening on Saturn. It's the beginning of its fall, as a matter of fact. Only its seasons last 7 and a fraction years. So we're seeing it right at that time, so the rings are edge on to us. It happens every 14 years. Beginning of Saturnian autumn and the beginning of Saturnian spring. They will slowly start to get wider the way we like to see them over the next couple of years. And even by 2028, they'll be significantly bigger than they are now, right? Reaching out, its maximum will be around 2032. And then they'll start shrinking back again, and it all repeats over the Saturnian orbital period, which is almost 29 and a half years. Okay. What's really cool and completely coincidental is right now, Saturn and Neptune are really close to each other in the sky, about a degree, which means if you've got 7 by 35 binoculars, which is the normal size. You can get them both in the same binocular view. So if you want to find Neptune, it's easy. Just find Saturn, which you can easily see. Put Saturn in your binoculars, look around for these stars, and there'll be a little faint blue star up there, somewhere along this line between September and December, and that's Neptune. Resolving it would take a rather large telescope, so mostly what you're ever going to see is just this bluish star. Another object in the same part of the sky is Ceres, the largest asteroid and a dwarf planet in our primary asteroid belt. It's in the constellation of Cetus, the sea monster that was going to devour Andromeda. And here's its path over the next 3 months. And it'll get closest to us as we go around in our orbit at the beginning of October. And it'll be in this field. This square here is this map down here. And it's about the same brightness as Neptune is. And so you can follow it along that arc. So at the beginning of, right around now, beginning of September, it's pretty close to these 3 bright stars, but it'll be a faint star along here. Even easier is Uranus, which coincidentally this year is right next to the Pleiades. This one's easy. This one I think everybody can do. If you put the Pleiades in your binoculars, look for these 2 stars. This Uranus is about the same brightness as these 2 stars. So if you can find these 2, see these 2, there'll be 1 extra star in there, and that'll be Uranus, which will look like a little green ball. To see it as a ball, you probably need a reasonably large telescope. What you won't see in this field is this star 38 Tauri. And this is a fun story. It showed up in an atlas that was done with measurements made in 1690 by Flamsteed, who put all the numbers on all the stars. So, 38 Tauri, 36 Tauri, all the ones in the Pleiades have numbers too. And he marked this little star 38, but it's not there. And does anybody want to have a guess at what it might have been? The first clue is it's right on the ecliptic. The second clue is 1690 is 336 years ago, which is 4 times 84. What has an 84-year period? Uranus. So when Flamsteed did his atlas in 1729, he actually marked Uranus by mistake, not knowing it was a planet. So he actually discovered it 60 years before it was discovered. And in 2026, it's going to be back over here again. So briefly, Uranus will be 38 Tauri once again until 84 years from now. The other thing I want to cover in the fall are the fall meteor showers. Now, the Perseids this year weren't so great because it was close to full moon. Not so with the meteor showers this fall. There are 3. There's the Orionids, the Taurids, and the Leonids. And I don't have the Taurids marked here because of the 3 of them, it's the least interesting. It also is happening during full moon. But the Orionids happen at the end of October. The Taurids are at the beginning of November, and the Leonids at the middle of November. The Leonids are probably one of the better meteor showers, and every 33 years, the orbit of the comet that produces this meteor shower intersects the orbit of the Earth in November. So you have a great concentration of meteors. In 1833, they had as many as 50,000 an hour. People thought the world was going to end. Hasn't been that great since. The last one was in 1999. I actually did manage to get up at 4 in the morning and drive to a remote location. And yeah, it was kind of like, there's one. Oh, there's one. Oh, there's one. It just sort of kept going. It was really, really great. The next one for that will be 2032, so we have a few more years, but it's still a great meteor shower.
If you were seeing a Leonid there's one.
But every 10 seconds, yeah.
10 seconds. Okay, so that's
Yeah.
400 plus an hour.
Yeah, it was the coolest meteor shower I've ever seen in my life. It's definitely worth getting up 4 a.m. for. Very few things are. But anyway, so and the cool thing about these is they don't all happen on one night. They'll happen over the course of a week. So basically from the middle of October to the middle of November, if you go out on a clear night, you've got a pretty good chance of seeing several meteors. Okay. Next time will be December 3rd. We're going to do the winter sky, where we get into Orion and Taurus. Jupiter comes back. We get to finally look at Jupiter after a year. All of our winter constellations. A lot more nebulae, lots of star clusters, and a few galaxies. So I hope you'll follow us on Facebook. Look for our public observing events. We've got one coming up, weather permitting, at the end of this month in September.
Yeah,
Yes.
I've got to say September since we can't.
Oh, right, we don't know. In September of 2025, there'll be a public event at the Greylock Visitor Center in Lanesboro. Thank you very much. And yep, our next meeting is October 1st. There are events coming up. Thank you again.
Thank you, Bob.
Question.
Yeah.
So you said you could see Saturn and Neptune in the same,
Field of view of binoculars.
but then you said you need something to resolve.
To resolve Neptune as anything other than a 7th magnitude star.
Oh, okay.
Yeah. But it definitely, the color sort of gives it away. Both for Uranus and Neptune. The color it's just not like a star.
You will also see a slight difference in that stars tend to twinkle.
A little bit more, yeah, and the planets don't. It's really freaky with Uranus. I mean, it really does look green, and there's just not much else in the sky that has that color.
I have a question.
Yay.
For the September 29th, 26th thingy, do you have, like, I have my telescope, and do you have details of when to meet up there?
We can talk about that after.
Okay.
Yeah.
Okay.
Because you're running that show.
For after your lecture, you mean?
Yeah.
Yes.
Yeah.
The lecture will occur regardless of the weather, but
Yeah.
the telescope observing will be weather dependent.